Okay. All right, so remember that I did explain to my tutorial group, though the tests are being marked as we speak, so obviously your test was last week. I've given my markers until this Friday to finish the marking and get them back to me. As soon as they're actually in my possession, I'll send a message out saying it's been marked and your marks are, we're going to use the CS mark system like we usually do in maths, and I'll upload solutions as well. Your mark might already be up there, but my markers usually put them in as they go. So although your marks may or may not be there, they're not all done yet, and I don't actually physically have them back yet, right? So wait until I send the message out to say they're done before you ask me, can I grab it? Can you have a look at it if there's a mistake, that sort of thing, all right? And I'll upload the solutions and stuff as well. All right, so what we're going to look at this week, the plan is that we're going to finish off all the stuff about vector fields this week, and then next week we'll start looking at something completely different, which is basically partial differential equations and Fourier series. So hopefully we'll finish everything off with the we need for vector fields this week. So cool, what we've basically been doing is we've been looking at vector fields, and we were calculating a thing we call the circulation of a vector field, and that worked in 2 dimensions or 3 dimensions. We just come up with a suitable parameterization. And the physical analog is if you imagine there's like a wire through space and you're pushing a bead or something along it, it's the force that's always tangential to it. And that's the circulation. The other one we did was the flux. However, the flux is strictly a 2D thing, right? And the flux is the force that's pulling, say, in 2 dimensions. You've got some curve in 2 dimensions, you've got a bead on it. The flux is the force that's pushing it off, and the normal always points out. Now, the reason that doesn't have a 3D analog is that if you have a curve going in 3 dimensions, what do you mean by out? Right? Now, a circle or so, it's obvious which one is in and which one is out. But if you have a curve in 3 dimensions, what do we mean by out? Right? To do that properly, you need much more advanced geometric stuff, or you do it through surfaces, right? So we haven't done the flux through a surface because we need something called a surface integral, which we're going to get to today. Today we're basically the 3 most important theorems in vector calculus in terms of integrating and finding circulation and flux. They're Green's theorem, Stokes' theorem, and Gauss's theorem. So they're named after 3 people, obviously, with those names. First one we're going to do is Green's theorem. So for the moment, let's stick in 2 dimensions. Right? Now, let's recall that if I've got a vector field in 2 dimensions, so it's x components, y components are both functions of x and y, and some curve C, this, without the circle, is the circulation, right? The shorthand for the circulation. The way we do it is we write this as... we come up with a suitable parameterization. This is basically f times the norm of this position vector r, and we integrate from t equals a to b or whatever it is. Right, now in this case we're only looking at curves that are closed, so they're ones that come back on them, so things like circles and things like that. So the start and the end points are the same, okay? And so when we do closed ones, sometimes, although when I was doing it before I don't, but when I'm applying this theorem I do, to remind myself it must be closed for this theorem to apply. Right, so this Green's theorem only applies to calculating circulation of a 2D vector field over a closed curve. Hence I always include the circle. Or you might remember there was a question, one of the questions in the workshop problems, we can write it like this. And we'll see why this makes sense in a hand-wavy sort of way a bit later on. Right? But basically we've got these 2 integrals. Now, since C is closed, it has an inside. Right? Let's call that D. Right? So remember, this is all 2-dimensional here. So we've got some closed curve. We go anti-clockwise as normal, but it has an interior, right? Region D. Right? That's obviously an area of some description. Green's theorem states that, provided these 2 components of this vector field are nice and well behaved, so continuous, so they don't blow up anywhere on C or in C, so they're continuous on C and on D, basically. right? So they're nice, with nothing blows up, no square roots and negatives, none of that crap, right? Then the circulation can be turned into a double integral, right? So the circulation around a closed curve C is the same as a double integral of this thing, right, which is the y component differentiated with respect to x minus the x component differentiated with respect to y. As always, this will be on the formula sheet. Don't stuff the order of the, take note of the derivative. The first component, x, and the sign as well. Second component with respect to x minus the first component with respect to y. So this is a double integral of this surface, right, so this is a function we get from the vector field, over the region D that lies inside C. Now, you might think, well, you know, why would I want to turn this integral, which I can do sometimes, into a double? Well, it depends. Sometimes, if we especially think back to the test last week, one of the questions I gave you is you had to find the circulation of a vector field around a triangle, yeah? You remember? That's 3 pieces, right? I could do those 3 as one double integral over the whole triangle. Right, that's where it becomes handy, right? But only if the curve is closed. To prove this, right, bit of hand-wavy proof, but it gets the idea across. Let's say we've got some closed region C, and I'm going to, because I want to do it, I'm going to do the double integral first, right? Let's say I split this, you know, at some horizontal line that I choose that's convenient. I'm going anti-clockwise, so let's say that x is from A to B. This lower bit, let's assume I can write this as y equals some function of x. And the top bit I can write as some other function of x. And I perform the double integral as, let's say I ask, what is the double integral of this function, partial dm dy, whatever the hell it is, right? Now, because the way I've set this up, I'm going to integrate y going from here to here, and then x is a big sweep going from here to here, yeah? So, and notice I've got this minus sign out here for reasons that will become apparent in a minute. So, bringing the minus 1 along, I've got x going from A to B, y going from this function to this function, and I'm going to double into whatever this function partial dm dy is. But the good thing is, because I've chosen to do it with respect to y first, I can do the first iterate. Alright? So this is just this function at this y minus this function at this y. Now, these two minuses make a plus, yeah? Right, so this first bit, the integral from A to B of this thing, now this is minus the integral from A to B, which I'm going to write as plus the integral from B to A. I'm going backwards. Now, what I'm basically doing is, I'm going anti-clockwise. So this first bit is the integral of from A to B along this curve, yeah? And then the second one, this is the integral from B to A along this, so I'm going in this, you know, I'm going anti-clockwise as I meant to, yes? That means these are the same thing, exactly, entirely equivalent to these path integrals, right? And of course, the path integral along this one plus half part on this one is the whole thing C, right? I can do the same thing to work out what is the double integral of partial dn dx. Right, so this time I split this region up this way. So here I now have x going from this curve to this curve. Let's say this curve is some function of y to some function of y. And then y as a big sweep goes from C to D. Right? So the double integral of this is x going from h1 to h2. Right? Because it's partial dn dx, I can undo that straight away as the first iterate. Now I clean this up. I've got the integral of from D to C along h1. So from D, so backwards, right? Hence why this bit, this minus sign becomes a plus, right? And then this one is just along this, whoops. This one from C to D along this curve, right? And I get that. So if I add them all up, I could say that this plus this is equal to this plus this, which is precisely Green's theorem. Okay? All right, so that's a proof. Now, this all hinges on a couple of things. One, that you can split the curve once, the region, sorry, once and only once. Right? If you've got one that you can't, so if it sort of doubles back on itself, you have to do lots and lots of but you get the proof work, you get the idea. We're engineers and applied mathematicians, we don't worry about details of the proof, it feels right. Right? That's how applied mathematicians look at these things. Right? Right, so we got this, and remember, as always, I'll give this to you on the formula sheet. Now here's an example. Why would you want to do this? Well, one is like the example in the test, or not example, the question in the test last week where you were calculating the circulation along a triangle. That requires 3 path integrals, but it's closed, means I could do it with Green's theorem with 1 double integral. It also helps if the parameterization's not nice. Right? So here's here's an interesting example. Let's say we haven't done Green's theorem yet. I asked you to calculate the circulation of this vector field over this curve with this equation. It's a circle of radius 2 centred at, say, x equals 1 and y equals 5. Right? Now, if I wanted to do this the old way, and I'm going to cheat, but if I wanted to do this the old way, can everyone see this bit still? Yeah? Right, first I would have, if I wanted to parameterize this, I could write that the x component is right, because then x minus 1 all squared plus y minus 5 all squared is 4 cos squared plus 4 sine squared, that's 4. Yeah? Right, so that parameterization will do it. Right, remember, if it's something squared plus something squared equals 1, we try and use the circle to help us out. Right, so that would be my parameterization. Then you remember how we do it. I need the derivatives and evaluate f at all of these, right? So what I would have is the dot product. What f is, x component is x to the power of 5 plus 3 times y. The dot product with the derivative of 1 plus 2 cos of t is minus 2 times sine of t, plus the dot product of the y bits, which are 2 times x minus y cubed, times the derivative of the y bit, and something's wrong. What's wrong? Oh, thank you, that should be 2 times sine of t. Derivative is 2 times cos of t. 2, not s. Oh, I'm on fire. There we go. Right, which is that awful thing. Right, now, you could do it by hand. Have fun. But you could. Right? Obviously, you've got there's straight away a substitution, awful substitution, right, it's a massive substitution. Oh, and there's a sine squared, so there's a half angle. But you could. Right? Because the last step, of course, is you integrate this. Right? Yeah, and you can do it. You could do it, right? It'd take you a long time to do it by hand, but you could. Yes? Right? We get the answer as minus 4 times pi. Okay. But notice the first thing, it's a circle, so it's closed. So I could, and the partial derivatives are nice, well behaved, so Green's theorem applies. So what Green's theorem says that the circulation, instead of doing it directly, do it as a double integral over this circle of this function, which you find. Yes? Right? And of course, partial dm dy is 3, partial dn dx is 2. Don't stuff up whoever's talking, quiet please. Right? Don't stuff up which derivative's which, otherwise you could end up something you can't integrate, or you're going to make the question much harder than I anticipated. Right, this one's nice and easy. Basically, you get so the region D, you're just integrating over this circle in the xy plane, right? But of course you're integrating minus 1. Right? Let's think of this as minus of this thing. And remember, if there's a 1 there, this double integral is actually the area of the region. Right, so this is just a circle. So I can cheat. Circle of radius 2, much easier. And what's even more interesting is that, notice that this part here, I've said that partial dm dy is 3 and partial dn dx is 2. So let's say I changed this. So let's say that this bit, instead of being x to the 5 plus 3y, let's say I made it 3 times y to the 10 for the hell of it. Oh dear. That's not right. Partial, oh, hang on, how have I started? Partial dn, whoops, no, I don't want to change that one. This one. Right, the y component. Let's say the vector field is x to the 5 plus 2x minus what y to the 10, say, right? You could do it, have fun. Now the reason, of course, is the same answer is because changing this doesn't change this, does it? Partial dn doesn't do anything. And I actually stole this question from a textbook where it was e to the y cubed, not y cubed, right? Now, if that was e to the y cubed, none of this changes, right? Because partial doesn't affect the answer, does it? Yeah? But if I asked, that's Maple saying I give up, right? Because it can't be done. You can't integrate e to this awful crap cubed, right? It can't be done. So here's one where this one's impossible. So unlike, you know, when we do double integrals, so you can do them 2 ways. One way might be possible, one way might not be possible. That's not really true. Both, if what can be done one way, can be done the other way, but doing it one way might involve functions or techniques you don't know about, right? Whereas this one is genuinely one where doing it one way is impossible, right? But the other way is. That's why these theorems are so important, okay? Right. Right, but all you have to check is just that curve is closed and the partial derivatives are well behaved in the region you've got to do the double integral over. You don't want things blowing up, okay? All right, but very, very useful theorem, right? Because sometimes the double will be easier. Let's have a look at a quick example. All right? Just so we can see it done from start to finish. So, as always, I will scan these, so you don't have to... What week are we in? 5. So let's calculate... Right, this is another one, right? A bit like the one I was talking about before. Now, first thing you should do, especially if you're doing a 2D one, just quickly sketch. So you've got basically y equals x squared right? And so if I was to do this, can everyone see that all right? Yeah? If I was to do this, I would have to parameterize let's say the y equals x squared, I could have x equals t. So y is t squared, t is going from 0 to 1. Remember, I need to go anti-clockwise. So I'm going there and then back along here. That would require 2 line integrals, wouldn't it? And I have to make sure I'm going anti-clockwise. Right? The first thing to notice is the region is closed. So, right, that's step 1. That means I may be able to apply Green's theorem. Right? And of course, obviously this is the point. Now, let's say that this is M and N. Don't stuff the order of which one's which. I'll give you Green's theorem on the formula sheet so you don't have to they're perfectly well behaved, nothing blowing up, nothing stupid, right? So instead of doing 2 path integrals, one say along the parabola and one then the straight line, or I could go straight line then parabola, as long as I go anti-clockwise, it makes no freaking difference, right? I could do it as one double integral. So it's, and again, even I've got to look it up, n dx minus m dy. I always mix the signs up. All right, so this minus this, what do we get? We just get x minus 2y. Right, so just standard double integral. Right, which I could do as completely up to you how you do it. Always handy to avoid square roots if you can. Right, so if I do y first, y small sweep going from x squared to x going from 0 to 1. And when you do it, right, it's a relatively simple thing to calculate. Of course, you know, first iterate's what xy minus y squared, you know, the laborious algebra, blah, blah, blah. But that is much easier than doing it as 2 line integrals, isn't it? Right? And if you think about the question, say, from the test last week, that was 3 pieces of the triangle. That's 3 line integrals. Or you could do it as one surface integral, one double integral, provided everything's well behaved, the partial derivatives are, and what you're integrating is continuous. That's the only thing to check. And the curve is closed. Right? So it's just an alternate way of doing it. Okay? Green's theorem actually has a lot of other applications as well. One in particular is, think about what it's doing. Right? Let's have, oh, I'm sorry, that's my screensaver obviously. Let's look at carefully what it's saying. This works both ways. Right? This is saying, yes, given a path integral of a vector field can be thought of as a double integral, right, which is essentially areas and volumes, yeah? But it also means the opposite's true. Right? Given a double integral, you could think of that as a path integral. And that can be handy, right? Well, let's say you've got a double integral over a circle of something, whatever the hell it is, right? It might be easier to, instead of doing the double integral over this area of the circle, if you turn it this way, all you need is what the thing's doing on the circle, right? So you can use only information along a boundary of a region instead of the whole region, and that might be advantageous. All you have to do is come up with a vector field that will do what you want, right? There'll be a question in the workshop problems tomorrow that explain that. So it's very, very useful theorem, this one, right? But the main thing is to check your curve is closed and your the double integral you create is doable, like as in it doesn't do anything naughty, yeah? Okay. All right, so that one's fairly straightforward. Green's theorem's fairly straightforward. All right, let's have a look at the next one, which is Stokes' theorem. Right, before we get there though, we need to introduce a concept of something called a surface integral. Now, if you did Math 1001, or I think it was either Math 001 or 1002, the old ones when we had 13-week semesters, you would have done surface integrals. Has anyone done surface integrals? Right, a couple have. Right, so if you did the new units after we took that out, right? So I'm going to be very hand-wavy about what a surface integral is, right? So because I'm not going to get bogged down with the details. But before we get there, we have Green's theorem can be written in two other forms, which we call the vector forms of Green's theorem. You might, if you're following along with a textbook or Googling or something, you might come across these different forms, right? The first one we're going to do is the tangential form of Green's theorem. We're not going to use it directly. I'm just going to show you what it says. Now, Green's theorem is a strictly two-dimensional thing, right? So, yes, we can calculate the circulation of a vector field in 2 or 3 dimensions the long way as path integrals. Green's theorem only works on 2D ones, but there is a theorem, Stokes' theorem, for 3D vector fields, for 3D path integrals of circulation of vector fields. Right? Remember, there is a trick. If I ask you what is the curl of a 2D vector, technically it doesn't exist, but we might need it for something. What we do is we think of a 2D vector as a special case of a 3D vector with no z component. Remember, the reason the curl doesn't exist in for 2D vectors is the curl is cross product, right? So cross product of two vectors is a vector perpendicular to both. So in 2 dimensions, you have 2 vectors lying in the plane. The third one's got to point out in the dimension that's not there. That's why it doesn't exist. But if you think of a 2D vector as a special case of a 3D vector with no z component, basically, right? I can calculate the curl of this fine. We did this a few weeks ago, right? And it's a vector pointing in the z direction, which makes sense. You've got 2 vectors in the x, y. You need a vector perpendicular to both. It's got to point up or down, wherever, right? Right, so first thing to notice is, oh, that term looks familiar. Interesting. Right? Now, this is a vector, of course. Now, let's say I dot product this with the unit vector in the z direction, 0, 0, 1. Right, make life easy. The dot product of these two is just this bit, isn't it? Which is this bit. So I could say the Green's theorem for a vector field f that's something, something, 0, right, can also be written like this. Right? So it's the curl of this vector field dot producted with a normal. Right? Because remember, this region D is a region in the xy plane. A normal to a region in the xy plane is just pointing in the z direction, isn't it? Yeah? All right, if I'm going anti-clockwise, I need the normal pointing up. We'll go through that orientation thing in a moment. All right? Now, this is called the tangential form of Green's theorem, which we're not going to use directly. Right? It equates the line integral of the tangential components of f to the area integral of the vertical component of its curl. Right? It's also called the circulation curl form of Green's theorem, a different notation. Now, let's say I have a general 3D vector field. Right? Now, yes, I can calculate the circulation around a closed curve in 3 dimensions using a path integral, but can I do that as a double integral as well if I want? Right? And it turns out you can. So that in general, instead of having a region in the xy plane and a normal to a region in the xy plane is k, I could have some region and a normal to it. Right? And it may not line up in the xy plane, may point in any direction, which I write like this. This is called a surface integral. Right? So for a 3-dimensional vector field, Stokes' theorem, which is an extension of Green's theorem to 3 dimensions, says this. Right? So normally we do double integrals over a region in the xy plane, dA, where dA is either dx times dy or dy times dx. What this is imagine you have a region that it's not in the it's not in the XY plane, it's sitting somewhere else. Let's keep it simple. Let's say we've got a sphere, right? And you want to do a double integral over a portion of that sphere, right? Now, what you could do is do a change of coordinates. Never works, right? Because the surfaces are usually bad. Or you define it as a surface integral. Surface integrals are awful things to deal with. So I'm going to show you the way we do it when we project things into the XY plane, right? But this, with all these S's here, this is a surface integral. Basically, we've got this situation. Now, obviously, drawing 3D on 2D doesn't work. What this is imagine I've got some surface S, and forgive the crappy diagram, right? I stole that from my colleague, but yeah, it sucks, right? Let's say we've got some surface S that's sitting, where the edge of it is some single curve C, right? What this is saying, and for S, I can find a normal, which I'll go how to do that in a sec. Now, if the surface S is, say, a function of x and y, like we did in multivariable calculus, we already know how to calculate a normal, which I'll refresh your memory about in a sec. Right, so a surface integral is basically, let's say there's a little patch of area sitting on this surface. I want to find the integral of some surface sitting above this one, a volume bound by a surface that's, say, beyond this one, bound by that surface and a patch of this one's surface. You get what I mean? So that's what a surface integral is, and it gets very hairy because you can't really visualise, unless the surfaces are simple, you can't really visualise what's going on. Right? But basically, what the problem we've got is instead of let's say I've got some curve C in 3D, right, and I've got some vector field. This is embedded in some 3D vector field, and I want to calculate the circulation of some vector field along this curve C, right? But for some reason I can't, or I've got to split it up into tons of pieces or something like that, right? What this is saying is instead of doing that, I can think of this as the surface integral of this over this surface S. That's basically what it's saying, all right? Now, let's go through another hand-wavy proof, and then I'll show you the form we're going to be actually doing this with, which isn't that one. Let's say we've got some surface S defined by some function, standard multivariable calculus function of x and y. Z is a function of x and y, which has some, I've got some curve C that I want to find a path integral of for a vector field. Right, and I work out what the projection is into the xy plane, right? The same thing we do when we're doing double and triple integrals, right? Projection of C into the xy plane is C1, it's basically setting z equals 0. And this surface has a projection D in the xy plane. Now, going through a hell of a lot of algebra, if I've got a 3D vector field, right, and because I'm restricting myself to surfaces that I can say z equals a function of x and y, and I'm going to project down into the xy plane, I can use tricks with the chain rule and things like that, right, to work out what derivatives with respect to x are, say. So imagine in my xy plane I can write things as y equals a function of x. This is not a rigorous proof, right, very hand-wavy. Right, but basically this awful looking path integral for 3D, I can replace this dz bit with this using the chain rule, so I can have it as dx and dy. Right, now it's like Green's theorem. Right, I can think this is a vector field where this is its x component and this is its y component. Remember, I know what z is, right, it'd be given in the question. Right, and I can apply Green's theorem to this, so I need the partial derivative of this with respect to x minus the partial derivative of this with respect to y. Lots of chain rules and crap like that. We ain't ever going to do this again. I'm not going to get you to regurgitate this proof. Right, but basically do all these derivatives, I've got chain rules, I've got functions within functions, it's freaking awful. Right, sit down and go through it carefully. Right, just to prove to yourself that it works. But basically, you clean it all up, lots of algebra, lots of chain rules, etc., etc., etc. you'll get down to this thing, right, that says this is the path integral you're after. Right? And if you squint and look at that long enough, you'll notice that I can think of that as this is the curl of this vector field, because remember f is P, or what did I say? I don't want to stuff the order up. MNP, right, these are the curls dotted with this thing. Now, hopefully from multivariable calculus, that looks familiar, right? Remember, if given a surface, remember when we found the equations of tangent planes, remember all that stuff? Right? And the way you do it is basically, the way, if you've got some surface and you want to find the equation of a tangent plane, what do? Remember, you've got function of two variables, you've got two vectors that are their partial derivatives with respect to x and y. So you know, all you know about this plane is two vectors that lie in it. Yeah? What you do from those two is you find a vector that's tangent to the plane by finding their cross product, and that's a normal, which is this, right? So that's a normal vector to a surface that will always point in the correct direction for us, for our purposes, right? So, but this looks messy. This is what we call a shorthand way of a surface integral. It's dotted with a normal over some area element, right? And when we switch to doing things where we've got surfaces of z, right, this surface integral simplifies to this expression. So this is how we're going to use this theorem. We're not going to calculate the surface integral directly, because I haven't shown you how to do it. But it turns out that when you do a surface integral over the xy plane, this is what happens. Okay? But you sort of see what I mean. Here you've got curl of dotted with a normal vector. Right? And that's what we write a shorthand as this. This handles any surface, not just one that's... Because you remember there are surfaces that... think back when you do triple integrals. If you don't project with respect to z first, you can project, say, with respect to y first. Then you need it bound by two surfaces. Y goes from a function of x and z to y equals some other function of x, z. And then you project into the xz plane, yeah? Same thing, right? That's why a surface integral written like this, I can project any way I want. But we're going to only project one way, and that's into the xy plane, right? So I'm going to use this simpler one, right? So this is in practice how we're going to do it, right? So we've got to unpack what this is saying. Given a vector field f in 3 dimensions over some closed curve C in 3 dimensions that we can hopefully parameterize in a certain way, the circulation, I can therefore instead think of it as a double integral over the region D, which is C projected into the xy plane, right? And C is the edge of some surface z equals a function of x and y. So I can figure out the projection in the xy plane, that's D. And then I find the dot product of the gradient, the curl of f with this vector. And I'm going to give you this formula on the formula sheet so you don't have to memorise it. Right? So this normal, we're going to always use this one as the normal. Okay? That's all I'm saying. Right? And then it's a standard double integral over a region in the xy plane like we're used to. Now, of course, there's an issue here though. Well, what I'm integrating here, the whole thing has to be z equals something involving only x and y. But if f's a 3D vector field, there's z's going to be in there. You use the surface condition to get rid of the z. Right? So we calculate curl of f in the usual way, come up with that 3 by 3 matrix, find its determinant, etc., etc. But once you've done that, any z's that are left, you use the surface you're doing it over to get rid of the z. Right? Let's have a look at this one. I'll turn this around a different way. Let's say I've given you this vector field, x squared minus y squared minus z squared, and z squared minus x squared. So I've got a 3D vector field, and I want you to calculate the circulation over region that's the plane x plus y plus z equals 1. So you could think of it like so. So that's 1, 0, 0. All right, so this plane x plus y plus z equals 1. Oh, you can't see. All right, so essentially what I'm asking in this question is find the circulation of this vector field over that curve C. All right, first problem. C1, C2, C3. I've got to split it into 3. I have to parameterise each piece. I have to make sure that when I project in the xy plane, I'm basically going anti-clockwise. Too much effort. Right? Instead, I can think of this as a double integral of something integrated over this region in the xy plane. Right? The bit under the surface. Right? So the surface is the whole triangle thing. Right? Its boundary is the curve C. Right? I need to figure out what they look like in the xy plane. Right? And essentially it becomes from setting z equals 0 because I've got the equation of the surface. Right? Right? So instead of doing this as 3 path integrals in 3D with 3 different parameterizations and all this terrible algebra, let's use Stokes' theorem instead. And of course, if I do it as path integral, I've got to make sure I'm going in the right direction and all that rubbish. Right? Let's use Stokes' theorem instead. So what Stokes' theorem tells us, that in most textbooks I said it's written in this form, but we're going to use a special case of it, which is this one, and only this one, right? Because I haven't shown you how to do surface integrals in other projections. Right? So basically what this is saying is that I need to calculate this thing. Yeah? First, and then do a double integral. Right, so I calculate its curl first. Right? We know how to do that now, hopefully. Right? And it turns out the curl is 2z, 2x and 2y. Right? It's a vector. Now, z, my surface is x plus y plus z equals 1. I want that as z equals a function of x and y. Right? Easy to do. Z is 1 minus x minus y. So this z here, I'm constraining it to lie on the surface basically because I'm only interested in what the vector field's doing on this surface. I don't give a crap what it's doing everywhere else. Right? So I replace any z's in here I replace with this surface condition. I find a normal to the surface, which is given by this formula, which is what we were doing a lot in MATH3011. So partial dz dx minus partial dz dy minus partial dz dx minus partial dz dy in 1, and it turns out that's the vector 1, 1, 1. All right? You find their dot product. Ooh, nice. Right? Nice when it's a constant. Right? And of course what Stokes' theorem says is you do this, the double integral of this thing, which is just 2, over a region D of the xy plane. Of course, now in the xy plane, you've got the region is x plus y equals 1. Right? So this bit down here. Right? So in the xy plane, it's really straightforward. You've got the line y equals 1 minus x. Right? And then you can do the double whichever way you want. How have I done it? I think I've done it. So y goes from here to here, and then x is your big sweep, goes from here to here. You could do it either way, of course. Right? And it turns out it's 1. Far simpler. Far simpler than doing it. You know, this is what the projection D looks like, and of course this is just. Right? But that's come out far quicker than doing 3 separate path integrals with 3 separate parameterizations, etc., etc. Right? So it's like the Green's theorem. Stokes' theorem is like Green's theorem in 3D. Right? So Green's theorem lets us work out circulations of vector fields in 2D via a double integral. And Stokes' theorem lets us work out circulations of vector fields in 3D via a special type of double integral called a surface integral, but we're going to do it as standard doubles. We're not going to do it the long way. Oh, sorry, not the long way, the full-on surface integral theorem way, because we haven't done it. Okay? But the key, it's very mechanical, right? Green's theorem and Stokes' theorem are quite mechanical. Okay? Let's have a look at an example, just so we can get a feel for doing it by hand. So this will be example set 2. Let's calculate the circulation of this vector field, so a 3D one, where C is the boundary of the parabolic cylinder Right. Now, what do we do? So we've got some, sitting in 3D, we've got some vector field that's explaining, say, the force at every point, say, in this room. Right? And I've got some closed curve that goes through the room. Imagine I'm running a bead along it or something, and I want, say, what we were looking at in the workshops last week, I want to calculate the work. Right? Now, what does this region look like? Well, and again, excuse my terrible, I can't draw to save myself. Now, the parabolic cylinder, so it's basically it looks like, oh, this is going to be fun. Basically, we've got some, all right, so this is a part of the surface. It's basically a, because the z is 1 minus x squared is a parabola in the xz plane. Since there's no y bit, it's basically like a parabolic cylinder that just keeps going. Yeah? And I only want a piece of it. Right? So I basically got y going from, I haven't drawn this to scale, y going from -2 to 2 and x going from 0 to 1. Remember, x is meant to be coming out of the page. Now, if you wanted to do this the normal way, it's going to require 4 path integrals. 1, 2. All right, so you'd have to have a piece that's where, what's that? That's x is going, that's the curve x is 1, z is 0, y goes from -2 to 2. Easy to parameterise. Then this bit is what? So you could say that z is 1 minus t squared, where t is going from, I have to go backwards to go anti-clockwise, so 1 to 0. Y is fixed at 2, then, right? All those different parameters, that's 4 path integrals. The hell with that. What Stokes' theorem says instead is that I can think of this as a double integral of the projection of this region into the, which is just a nice rectangle. Yeah? Right, and all I need to do is calculate all of this stuff. Right, and then just do the double integral. Okay? So, as with the lecture notes, the first thing to do you need its curl. You know, basically, you unpack what this is saying, right? I need the curl, right? So I need the curl of the vector field. When you do this, this will become make sure you check this. Right? I also need to construct a normal to this surface, which is what we used to do when I could have asked you, what is the equation of a tangent plane to this thing back in same thing. Right? I calculate this normal vector. So minus partial dz dx, right? I'm going to give you these formulas on the formula sheet so you don't have to memorise because you don't want to miss out a minus sign or anything. That's my surface, of course. Right? So this is just the vector. Right? Now the z bit's always 1 because I have chosen to do the double integral for functions of z. I'm always going to use this to project in the xy. Never going to do it any other way because otherwise the surface integral, I'd have to go back to the surface integral definition, which I don't want you to do. Right? So basically I figured out this bit and this bit. I can find their dot product pretty easily. Oh, that's because of my hand, yeah. Right? So what have I got? I've basically... Now, technically, I should get rid of this z. I should replace this with 1 minus x squared. But I don't need to. Right? Because it's multiplied by 0. That's why I didn't bother. Right? So what this says, now I'm going to do the double integral of this function over a region D, over this region D in the xy plane, which is basically the projection of this thing into the xy plane. As always, when we do double integrals, you should draw it. But of course, this one's relatively straightforward because the projection of this thing just this. All right? So then all I have to do here is that the circulation by Stokes' theorem is instead, so this is at my region D of this thing. Right, so it's just a matter of putting everything into this formula. Okay? And you can choose which way you want to do the sweeps. Rectangles are awesome. Doesn't matter which way you do it. So here I'm doing x first, then y. Of course, it doesn't matter. I could do y. When it's a rectangle, I could do it y then x. And when you do this, well, the key is doing that as a path integral would be a lot more work for the same answer. Right? The only time the theorem doesn't work is a bit like Green's theorem. The only time it would be bad is if this function you make from here blows up. Right? If it does something naughty inside this region D, then the theorem may or may not apply. Most of the time it will not apply. Something will go wrong. Right? So you sort of just check in the back of your mind that this surface, right, is perfectly well behaved directly above this region, right? Just as you would do with normal double integrals. Okay. All right, so these are basically just alternate ways of calculating the circulation of 2D and 3D vector fields. 2D is Green's, 3D Stokes, and Stokes is actually a special case of Green's, right? And as always, I'll give you the formula sheet. But when we did vector fields first, there was another thing that we calculated, which was the flux, right? So you might recall that when we did circulation and flux, this was how we calculated the flux, but this was strictly a 2D thing, right? So recall that the flux across a curve in 2 dimensions, so given some 2D vector field and some curve C in 2D with parameterization R is x of t, y is y of t, the flux of F across the curve, so this is like, you know, imagine a force, what force is trying to tug a bead off a wire, right? Whereas the circulation is what is the force that's pushing it along, this is what bit's trying to get it off, yeah? And it was given by this thing, which is what we did a few weeks ago, right? And we construct a specific normal, so it points out, yes? Right, now in 3 dimensions, the reason this doesn't work in 3D is that you don't want you want the flux through a surface now, right? Not just along a curve, right? So for a 3-dimensional vector field F, we say that the flux of F now through a surface. So imagine you've got some vector field in this room and there's, you know, vectors pointing left, right and centre. Imagine that I want to know what's that force doing just in this tail, on this, through here. Imagine this a vector field's describing how water flows through the room, or how the aircon's working, right? How the aircon's blowing the air through. And I want to know how much air is it pushing through, if this table was hollow, through here. That's the flux, right? So to do that, formally, the flux is defined as another surface integral, right? It's written this way is because it's basically, the writing it this way is so it's coordinate free. Then what you're meant to do is you say, well, if you're going to do it over a surface z equals f of x and y, you do this. If you're going to project it in the other way, you do this. We're always going to project one way, right? So just like these two, this is notice the thing, you've got some vector dotted with n ds is a surface integral, right? But if I'm going to do the double over the xy plane, then it's that same vector dotted with the normal of a surface z equals z equals function of x and y over now a region D in the xy plane, so this now just becomes a double integral like we're used to do it, right? And you'll notice that this one, same trick, right? So I'm only going to get you to do a specific type of surface integral, which is a standard double integral of some region over the xy plane. We're not going to do other ones because I haven't got time to go through the proper theory of surface integrals first. Okay. Right. So as with Stokes' theorem, this n is supposed to be a unit normal, but because I'm going to do it a specific way, we're going to use this formula. Okay. Right, so the flux of a vector field in 3D is the dot product of the vector field F with a normal to a surface. Right, so let's say this, I've got an equation that describes the surface of this thing. I need a normal vector to it, which is minus partial dz dx minus partial dz dy in 1. That will handle the orientation of things for me, so I don't have to worry about going in the wrong direction. Right? It basically means it's always pointing out. Right, so if it's a sphere, it's always pointing out. But if the curve's more complicated, what we mean by out is something to do with orientation. But when we do this one, it always works itself out. Okay? And as before, the vector field F is technically a function of x, y, and z. This is a double integral. Z shouldn't be there. Right? So what you do is you use whatever the surface you're doing. You're only interested in what the vector field's doing over a particular surface. Right, so you use that condition in the vector field, get rid of the z's, then do the integral as I've given. Okay. Right, so for example, to find, if let's say we've got this rather boring vector field which says it has no x bit and the y and the z bits are just linear functions of z, right? And I want the flux of this thing, right, through a plane in the first octant. Remember, that's just x greater than 0, y greater than 0, z greater than 0, right? Go through the process. First thing is I need a normal vector to this surface because I'm always going to do the surface integral over a region in the xy plane. So instead of using this nice general formula, I'm going to use this specific one each time. Right? I replace all instances of z with the condition. So this tells me what's the vector field doing only through this surface, because that's all I'm interested in. I don't care what it's doing everywhere else. Right, and it turns out that it replaces z with 6 minus 3x minus 2y. I need minus partial dz, the vector minus normal vector to the surface. That's just 3, 2, 1. Then I plug everything in. So the flux is the double integral of this dot product, which we work this out. It's 3 times 0 plus 2 times 6 minus 3x minus 2y plus 1 times, right? And you get this 18 minus 9x minus 6y. Right? And then I'm going to do this double integral over the projection of this plane in the xy plane, of course. So in the xy plane is that equals 0, isn't it? Right? So what is it? It's y equals 3 minus 3 on 2x, say. Right? So it's basically a triangle. Right? And then you do small sweep, big sweep. Right? And off you go. Okay. All right, so this lets us now work it. Now we can calculate fluxes in 2 and 3 dimensions. So 2 dimensions we just use path integrals. 3 dimensions we use technically surface integrals, but we're doing a specific surface integral, 1 over the xy plane. All right, so let's have a look at an example of this. Again, this one's also quite mechanical, right? Oh, no, we're not. We're not doing that yet. Right. Sorry, we're not doing that yet. All right, so this basically lets us calculate, you know, the flux of 3D. So now, if we want circulation, you can do it as a path integral that works in 2 dimensions or 3 dimensions, or in 2 dimensions and you curve the curve C is closed, you can use Green's theorem, or in 3 dimensions over a closed curve, you can use Stokes's theorem. Right? For the flux, for a 2D version, we only ever use the path integral one. There isn't really a theorem that well, there kind of is, but we never use it. Right? Actually, we're about to do it, but we never actually use it. Right? But for 3 dimensions, we've got this double integral. Now, let's think about this Stokes's theorem, which we're working out the circulation of a vector field in 3 dimensions, turns a single path integral into a double integral. So hopefully it's not too much of a leap to imagine that there might be a theorem that instead of doing a double integral for the flux, it's a triple integral over something. Right? And that is the last one, Gauss's theorem, right? Which we're going to work out is actually can be thought of as a triple integral. And it's another special case, kind of Green's theorem. I'm not going to go through the proof of this one because it's terrible, right? And just leap of faith and take my word for it, okay? All right, but remember I said there are 2 two what we call vector forms of Green's theorem. We did one, right, which was there, right, that says that the circulation of a vector field is related to the tangential bit. The normal bit. Right? Because this is the tangential form of, tangential form of Green's theorem. Oh, yes, right, because of circulation. Right. Now, let's go, right? Let's first off maybe explain this shorthand notation we're doing. This is extremely hand-wavy, right? But it's useful. It's like one of those things that, when you do the chain rule, as a standard function of a single variable. Let's say you got y equals f of x, and you let think of it as y equals some function of u, where u is some function of x, and we say dy dx is dy du times du dx, don't we? Right? We all know that by now. And one of the main reasons I prefer operator notation is that we think of it as a fraction. Although it isn't, right, it's useful to think of it that way. Right? Same thing here. This one's a bit hand-wavy, right? Because we think of the ordinary derivative as a fraction. Right? But where does this notation come from? Well, think formally, when we were doing circulations, this is how we did it. Right? We parameterize this is f evaluated along this curve, just like what we were doing before when we replaced z with the surface condition, dotted with a tangent vector. Right? Now, if we've got some parameterized curve in 2 dimensions to say x and y, right, then the derivative of the r dash or dr dt is basically dx dt dy dt. That's what we're used to doing. Right? Usually we call this r dash. Right? It's the only rare time I prefer dash notation. Right? But if I think of this as a fraction, not meant to, but it helps. Right? If I multiply, I can think of the dr bit as this times dt, so I multiply all this like dx dy. And so this notation kind of now makes sense. Right? This is like f is m and n, dr is a vector, say dx dy. So this is m times dx plus n times dy. That's where this shorthand notation comes from, basically. Right? So if dr is our tangent vector, then I want to find what is f dot dn, right? The flux of it, and we're in 2D here. Right? So you recall that when we did the flux a few weeks ago, right, that if r dash was c and d, the n I took was d n minus c. Right? Because remember, given a vector in 2 dimensions and you need a normal, there are 2 choices, aren't there? Right? There's, if your vector's like this, there's one that points up and there's one that points down, whatever up and down mean. Yeah? And which one we choose is the one I want it pointing out. Right? And if I go anti-clockwise, this one will always point out. Right? That's why we do it that way. That's the decision that's been made somewhere along the line. Right? But notice if its tangent vector is c and d, its normal is the y bit minus the x bit. Right? And there's another normal vector that's minus d and c, but that points in the wrong direction. It means my answer will be negative when it should be positive. That's all. So, if I've got this vector dx dy, this tiny little tangent vector dx dy, then the normal vector I want is dy minus dx, isn't it? Right? The y bit minus of the x bit. So I could say that in 2D, f dot dn, I could write in this notation instead. Or now I could forget this thing for the moment and just look at this. Well, I could say, instead, I could think of that as being minus n dx plus m dy. So that's the same as a path into, or the circulation of a vector field that's minus n and m. Right? Instead of being m and n, it's minus n and m. So I can apply Green's theorem to that, provided everything's continuous. Right? And I get, that looks like divergence. Right? So we had one old vector form that had the curl. Right? This is another one that's got divergence. This is called the normal form of Green's theorem, and we're never going to use it directly. Right? And so it equates a line integral of the normal component f to the area integral of the divergence of f, basically. Right? It's also called the flux divergence form of Green's theorems. So the previous one was circulation curl, because you're saying f dot dr equals something involving curl. This is saying f dot dn equals something involving divergence. Right? So flux divergence, basically. Right? Now, giant leap of faith here. If I add another integral sign to both sides, life is good. Yes? Trust me. Right? Right? So if this is saying f, the integral of f dot dn is this one. So the double integral of f dot dn, as in the surface integral, is the same as a triple. Right? That basically. Right? And you have to take my word for it. Right? It's a leap of faith basically, but it doesn't take too much to think. Well, if there's a 2D to 3D analogue, if there's a 2D to 3D version, there's probably a 1D to 2D version. There's probably a 2D to 3D one. Very unmath-like, but get the idea. Yes? So, let's go back for a moment. This is how we calculate the flux. What is this saying? We've got a 3D vector field F. I want to calculate the flux of that thing through some surface S, which is this, which I call a surface integral. But I'm doing a special case of this surface integral, which is this. I'm going to integrate this expression that I need to find, f dot this, where my surface's projection in the xy plane is d. Right, that's basically what I'm saying. Right? So let's say I've got some surface S, and technically it's defining some region in my 3D vector field because I want the flux through it, right? The three-dimensional analogue is let's say this surface is a slice of a next dimension up surface, like a solid, right? So think of a whole sphere. Let's say I wanted to calculate the flux through the surface of a sphere, right? Then the solid is the whole sphere itself, right? Just like Green's theorem, you've got curve on the outside and the solid inside, right? You relate the integral of C along the boundary to an integral over what's inside the boundary, right? So let's say you've got some surface now that's closed, like a ball, right? So it's got to be closed because it's linked to Green's theorem. So everything's got to be sealed, yes? Right, so you're looking at the solid inside, which I'm calling E. Doesn't matter what the hell you call it, right? Whatever it is, right? And it's got some normal that when it's a surface integral, you have to find an expression for this normal, which is extremely laborious, which is why I don't bother because it gets silly, but we're going to do a specific one, which is where our normal is, where is it? This one, right? Right, then Gauss's theorem says that the flux of a 3D vector field through some surface S, right? Surface S is the boundary of some solid in 3D, isn't it? Right? Let's think of spheres. So let's say I ask you a question, find the flux through a sphere, right? The formal definition says you need to do a surface integral of the flux vector, right, the 3D flux vector dotted with a suitably chosen normal. We're going to use one I'll give you, right, one for the surface, as a double integral of the projection of that surface in the xy plane. What Gauss's theorem says is instead do a triple integral over the whole solid inside that surface. That's what this is saying. Right? So, and it's divergence, right? Grad dot f. The proof is similar to the proofs the proofs I've given you for Green's and Stokes is a very hand-wavy. This one's even more hand-wavy, but it does follow the same idea. Just got lots of triple integrals to do, right? Which, we don't really want to do that if we don't have to. Right? Triple integrals get very laborious to do. Okay. And as before, I'll give you this formula as well. Right? But let me show why. Again, same question. Well, with Green's theorem, that's telling you for a 2D vector field, if you want the circulation, if the curve is closed but can't be described as a single equation, you've got to split the damn thing up, right? And do, think again, the question from the test last week over the triangle. If you had to do that as three separate, hopefully you all did it, as three separate path integrals. Now that we know Green's theorem, you could have done that as one double integral. Same thing here. Right? If you've got let's say I ask, well, instead of saying I want the flux of the vector field in the room, and instead of I want the flux through this table, through the surface of this table, let's say this table is a giant rectangle, and I want the flux, coming out of this surface, all 6 sides of this box. I would have to do 6 surface integrals. Ain't going to happen, right? Or I could do it as one triple integral, where the volume I'm integrating over is the whole box. It's inside, you see? Right? That's all it's saying. Here's a great classic example of how simple this makes life, because you might think, well, triples are never simple. Right? Surely that's not going to make life easy, but you might have thought the same with greens in a double integral. Right? Let's say we've got some vector field and I've got a unit cube. So let's say, first off, that this table's a cube, not a rectangular solid. This is the origin. We've got some vector describing something, maybe the flow of the aircon or something like that. And I want to know, what is it blowing into? Is all up, because the aircon's going all different directions. Is it blowing into the box or out of the box? Net. It's net effect, say, something like that. Right? So through the unit cube, x going from 0 to 1, y going from 0 to 1, z going 0 to 1. Now this cube's got 6 faces. That's doing it the previous way. That is 6 double integrals. Right? And to do it, I would need to find the equation of this face, this normal, this face, this normal, this, right? 6, 7, oh, the hell with that crap. Right? What this is saying is instead think of it as a triple integral of something. It turns out it's the divergence of your vector field over this solid. That's what a triple integral is. Right? You move a dimension up, just like a double integral is the volume bound by a surface and a region in the xy plane. A triple integral is the volume of a 4D surface but sitting above a 3D surface. You can't visualise what that is. No one can. Right? We live in through it. We can't visualise what 4 dimensions is, but we can do maths on it, of course. There is a famous physicist in the US that claims he can visualise in 4D. I call bullcrap, personally, but you never know. He is very smart. Anyway, if I wanted to do this the previous way, that is, I don't want to do 6. Right? Let's instead do it as one triple. Now the divergence, remember it's like partial, the first component with respect to x plus the second component with respect to y plus the third component with respect to z. Right? So remember, divergence gives a scalar from a vector field. Right? So it's basically just 2x plus 2y plus 2z is its divergence. Right? So that's the function you're doing a triple integral over this solid, which has awesomely easy limits. Right? It basically makes no difference which way you do it. I've decided, x first, then y, then z. Right? If it was a more complicated thing, right, it's where you can choose which way to project, but I'll probably keep Elysium z first. Right? Because, triples are like triple integrals getting to the point where it's just getting too tedious to do it by hand, unless it's simple. But you can do this instead of doing 6 separate ones, which if you did, you could do it, and you add them all up, you would get 3. Right? Believe it or not. Right? But here I can do it in one fell swoop. Yes, there's a lot of steps missing, but okay? All right, let's finish off with a couple of examples of all this. All right, so we've got example set 3. Page 4. All right, so let's calculate the flux of the vector field I can't read my own writing. through the surface in the first octant. Right, so we've got some 3D vector field. So and I've got to calculate the flux. Right, so imagine, you know, the corner's the origin. So this plane is something like that corner. You know, it'd be useful if this was flat, but that corner and that corner. So the plane that slices through in the first octant, x is 0, y is 0, z is 0. Right, and you want the flux through that surface only. Right? Notice first that you can't use Gauss's theorem, because I want it through a particular face, not through the whole pyramid. Right? You've got to read the question carefully. Right? If I wanted the flux through the whole solid, then I'd be asking through that triangle, that triangle, that triangle, and that triangle, wouldn't I? Right? It's a pyramid. It's a solid pyramid. Yeah? That's not what I'm asking. Right? Right? So the Gauss's theorem would give you the flux going out everywhere. I only want it through one face. Right? So this, we just use this definition. First thing I need is, because we're doing a specific case of the surface integral. Basically, we're doing the one this one, right, where I can project the surface I'm giving you can somehow, either I'll give it you as z is a function of x and y, or you rearrange it. Right? I'll give you ones that can be done, of course. Of course, this one can. Right? Looks like that. Right? So if I was to sort of, what am I doing? I'm not even going to attempt to draw a 3D vector field, but I can imagine it's a bunch of arrows pointing in a certain direction. At each point, at a particular point x, y, z, it looks 18 z minus 12 and 3y. Right? Right? Now this thing, what does this look like? So when z is 0, what's that? It's something like, not to scale, of course. Now when x and y is 0, z is 2. So this is when y and z is 0, I've got x is 6. Because I want the first octant. So that's x is 0, y is 0, z equals 0. And this is 4. All right? So basically, oof. Yes, that should be straight. Right? But I want the flux through just this triangle, right? Not the whole solid underneath it. Right? That's what I'm after. I need a normal. Right? In Math 1011, we covered how to do that. A normal to a surface is this every time. Right? It's guaranteed. So I find an expression for the normal vector. It's always this thing. So partial dz dx, that's e, and the minus sign, that's just a third. Partial dz dy, that's a half, and 1. And you can sort of think, well, does this make sense? Well, what's a normal? But it's basically got positive x, positive y, positive z. So the way I've drawn this, it's sort of pointing sort of that way, isn't it? Out of the, right? And it sort of doesn't take too much, with the angles set up. Yeah, feels about right. Right? That's what applied maths is a lot of the time. A lot of the time it is feel, which skill that comes with lots of practice. Right? So that's a normal vector. What I do is I find their dot product, that f dot n, right? but we're using a specific n, because I haven't shown you how to find the normal that points in the right direction in other doing a double integral over a different projected region. Right? Because it just gets too damn tedious. To be honest, it just gets too tedious. Even I don't do them anymore. Anyway, f dot n, that's easy. That's just this the vector field dotted with. Right, so basically, I'm just finding this thing. Clean this up. What do you get? You get, when you do it, that's basically 18z times a third plus minus 12 times a half plus 3y times 1. When you do it, you get that. Now, if there was a z still there, right, what I would do then is use this surface condition. Right, basically the surface, I'm only interested in what it's doing on this surface. I use that to get rid of it. I don't have to here, so it's fine. Right? Now what this thing says is I have to do this double integral over a region projecting this down in the xy plane. So think of this as a triple integral where I have chosen to integrate with respect to z first. Right? So z goes from 0 to 2 minus a third x minus a half y. What's the next step? What does this look like in the xy plane? It's the 2 minus a third x minus a half y equals 0, isn't it? Right? And you can figure out what it looks like. Right? Basically, it looks something like so in the xy plane, what have we got? We've got z is 0, so 2 minus the third x. What's this? This is y equals 4 minus 2/3 x. Yeah? Right, so what does that look like? Well, that's, remember, we've got to do a double. You should always, good habit to draw the region to figure out the sweeps. And when x equals 0, y is 4. When y is 0, x is come on brain, 6. Right. So this is the region I've got to do the double integral over. Right, sorry, I really should turn that off before I come to class. Right, so now we just do it. So now you've got to do the double integral of f dot n. And because I've already written y, let's say I do y goes from 0 to 4 minus 2/3 x, and then x goes from 0 to 6, doesn't it? Right, that's the integral I have to find. And you should find that it's that. Okay? All right, let's have a look at another one. So let's calculate the flux of the vector field through the cylinder x squared plus y squared equals 4 between z equals 0 and z equals 3. Right, look, think about, what does this say? Think carefully about what this is. Oh, I'm sorry. When that happens, somebody yell out, because obviously I don't have eyes in the back of my head. Right? What is this saying? So we've got some 3D vector field, right? Let's again say maybe it's describing the movement of the air in this room from the aircon. Right? And I've got this cylinder, x squared plus y squared equals 4. So we know in 2D that's a circle. So as a surface, you just no z component. It's just a cylinder that goes up and down in the z component, isn't it? Right? So basically, you've got, it looks kind of like this. And again, excuse the crappy drawing. I've never ever been able to draw well by hand. What would you prefer, good drawing, bad handwriting, or the other way around? Good handwriting, I would guess. Right? So you've got z from 0 to 3. So z is 0 is the xy plane. Basically, you've got a cylinder. Right, so this surface is that, and you're slicing it at 0, which is obviously the origin, and 3. Now, what I'm asking for is the flux coming in or going out. Right? Out will be positive, in will be negative. Right? That's the way we've orientated everything. If I wanted to do that like I did the previous question, I need 3 surface integrals, because I need the flux coming out of the cylinder surface, the flux coming out the lid, the flux, imagine it's a tin can, right? I need the flux coming out through the surface, coming out the lid coming down through the bottom, don't I? Right? I'd have to do, and I'm not going to, for flux in 3D, I'm not going to get you to do it more than once. Right? But these questions, probably in a test I would say, use Gauss's theorem. I tell you to do it. Yes? You won't have to do this one unless let's just say no, I'm not going to do that. Right? It's too tedious. Right? But I could do it that way if I wanted. Right? But instead, what I'm going to do instead is, what Gauss's theorem says is I can think of this as a triple integral of something, which turns out is the divergence of this vector field over that solid cylinder. That's what I'm doing. All right? Right, so first thing I should do is, because this tells me I need its divergence. So remember the shorthand notation, just to refresh your memory, is like this nabla vector dotted with, right, so this is, remember, a useful way to remember. So it's basically, what the hell just happened? Sorry, I think I turned the lamp off. Now I've lost my train of thought. That's too said. All right, so that's its divergence. Now I've got a z in here. All right, that's a bit of a problem. And something's wrong. Oh, yep, thank you. Right, now I need to integrate this thing, which I can't visualise. Remember, this is like a 4D surface, right? But I've got to do a triple integral. Now, looking at that, what's the smartest way to do it? Right, well, you could have z going from 0 to 3 as your first iterate, and then you squash it into the xy plane, don't you? Yeah? Right, so I could imagine that's the first iterate I've got right, and then the xy plane, I've got the circle, don't I? Right, and as always, you should draw it. Now, the presence of x squared plus y squared often indicates that we should switch to polar or cylindrical, right? But we don't actually have to in this one. Now, what you could do is you could say, well, I could say that sorry, again. Right? I could say, well, I could do this two ways, couldn't I? I could say, well, y goes from minus the square root of 4 minus x squared to plus the square root of 4 minus x squared, and x goes from minus 2 to 2, or the other way around, yeah? Or usually what you do is switch, right? Switching, usually if there's an x squared plus y squared that's screaming at you, use polar or cylindrical, right? Or this is a triple, you might use cylindrical to help, right? I'm being a bit lazy. But what you could do is just do it directly. It's actually smarter to do it in cylindrical, but it's the end of the day on Monday and I can't be bothered. So I could say that it's right, and of course, as always with triples, that technically there are 6 different ways you could do this. But I've decided to do it z, then y, then x. Right, that's the way I've done it. I've decided to do it. Right, and you just hope that it's doable. Now in my notes I've left all the steps out, and I cheated and used Maple to tell me what the answer is, so let's see if it works. Now, the first iterate with respect to z is, what's that? That's 4z minus 4yz plus z squared. Oh, that's from 3 to z goes from 3 to 0. I always do that so I don't substitute the wrong substitution. So z equals 0 is always handy, but again, please don't do it in your head. Or some of you do and tell me if I stuff it up. So what's that? That's 12 plus 9, so 21, because that's 0 is all 0 there, minus 12y. Ugh. Right. Now the awful bit, so this is 21y minus 6y squared. Oh, it had to be odd, didn't it? Freaking hell. So this will become, again, don't do this. Right. Now, how would you do the next one? Right? You'd have to use an inverse trig, wouldn't you? Or, pardon? No, you don't. No, but you could do as an inverse trig. Or, but remember what this is? This is 42 times the integral from minus 2 to 2 of 4 minus x squared. It's the area bound by that curve. It's a semicircle. Right, so I'm going to cheat now. Well, that's just times a half pi r squared. Right, if you do inverse trig, you will get the same answer. So you should get, which I hope is the answer Maple gave me. Right? Yes? Can we do that? Of course you can. Of course you can. Right? But a lot of the time with triples, you remember, you'd use, for doubles, sometimes switching to polar helps. Right? That'll all be explored in the workshop problems tomorrow. So as always, I'll upload these examples and the workshop problems first thing tomorrow morning. Okay? All right, we'll leave it there for today. Thanks, everybody. Yes, yeah, let me turn this off. Yep.